Lesson 7. This kind of ties everything together. This is the work-energy theorem. First of all, we defined energy as the ability to do what? So energy was the ability to do work. And what did we define work as? What was work equal to? Okay, energy was the ability to apply a force over a distance, which means if you have energy, you can do work even if they haven't given you a force and a distance. It seems to me there should be a way that I can figure out how much work we're capable of doing. That's what question 4b in the quiz was getting at. And this brings us to the work-energy theorem. So first of all, if they say to me, how much work? My hope, my first goal is I'd like to be able to go, don't write this down, force times distance. But the problem with that is it's very conditional. First of all, the force and the distance have to be in the same direction. Secondly, the force has to be a constant force. It's kind of limited. It's the easiest, times equals, but it's not the most useful. We also said that work was the area underneath a force versus distance graph. When do I use that? Well, probably if they give me a graph, then it will be, suppose it was moving from that distance to that distance, it would be that area. There is the third better definition of work, but it's my last resort because the other two are much cleaner, much nicer. But the third one is much more flexible. I was saying to Kessler earlier today that when we get to rocket science and orbits 2 units from now, you're going to find, we're going to be using this thing called the work-energy theorem to figure out how much energy to put stuff in orbit, how much rocket fuel to put stuff in orbit. But it's going to be one question, takes up literally an entire page, about 15 lines of, no pun intended, work. It's not the most convenient definition, but it's by far the most flexible. The work-energy theorem, the third way to calculate work equals the change in potential plus the change in kinetic energy. Where, what does change in anything mean? Something minus final minus initial. So work is the final potential energy minus the initial potential energy plus the final kinetic energy minus the initial potential kinetic energy. When do I use that? Well, if Annika, they say, how much work? But I don't see a force or a distance anywhere, but I see speeds or changes in height. I can do it then. So as an example, a cyclist weighs 65 kilograms. I should really say has a mass of 65 kilograms because weight is measured in newtons. I'll fix that next year. Her bike has a mass of 7.2 kilograms. So I'm pretty sure M is what, 72.2 kilograms? Yes? I'll jot that down so I don't accidentally write down the wrong mass. If she's pedaling over level ground, underline the phrase level ground. Ooh. Annika, what's this question asking me to find? No. How much work? Okay, so don't write this next bit down. My first thought would be, well, Annika, do you see a force or a distance anywhere in this question? My second thought would be, hey, maybe it's the area underneath a force versus distance graph. Did they give me a graph? Then I guess I'm going to use the work-energy theorem. Did I give you the work-energy theorem on your formula sheet? Okay. I used to make the kids memorize this one. I don't anymore. Work is going to be the change in potential energy plus the change in kinetic energy. Now, how can you have a change in gravitational potential energy? There has to have been a change in height. What 2 words did I underline? Is there a change in height? So what's the change in potential energy as a number exactly? Okay. Was there a change in speed? There was a change in kinetic energy. So this is going to end up being KE final minus KE initial. How much work? A half mv final squared. Well, you know what? In this case, what is the initial speed? So what's the initial kinetic energy? Does the m cancel here? No, and it shouldn't. It takes more energy for a heavy person to get up to this speed on a bike than for a little kid to get up to this speed on a bike. So it shouldn't cancel. There's a reason why little kids can run around like crazy and just seem like they never ever get tired. They're just not burning as much energy. And because they're not burning as much energy, they're generating less power. Power is tiredness. They're doing less work, so their work over time is less than our work over time. 0.5 times 72.2 times 5 squared. Point 5 times 72.2 times 5 squared. Do you get 902.5? Yeah, that's how many joules of work. That's how much energy left this cyclist's body, because the energy had to come from somewhere. Where did the cyclist's energy come from? The food that they ate. What about to increase her speed from 5 to 10? Notice in part A, by how many meters per second did we increase our speed? 5. In part B, by how many meters per second are we increasing our speed? 5. But it's going to take more work. This is where that squared on the V really starts to rear its ugly head. It's going to take more energy to go up another 5, way more energy. So it wants me to find work. I've already noticed that the change in potential is 0, so it's going to be KE final minus KE initial. This time none of these are 0, so it's going to end up being a half mv final squared minus a half mv initial squared. It's going to be 0.5 times 72.2 times 10 squared minus 0.5 times 72.2 times 5 squared. Point 5 times 72.2 times 10 squared minus 0.5 times 72.2 times 5 squared. And I find, do you get 2707.5? I'm going to keep all the sig figs just so I can notice a little pattern. So is that right? 2707.5? People nodding? Joules. How many times more? Well, if I go divide by 902.5, 2707.5 divided by 902.5, 3 times more. Mr. Dewick, I thought twice as fast was 4 times as much, but we didn't start at 0. If we started at 0, it would be 4 times as much. Here's 1 times as much, 3 times as much. There's your 4 times as much from 0. What about from 10 to 15? Going to be more. It's going to be a half mv final squared minus a half mv initial squared. It's going to be 0.5 times 72.2 times 15 squared minus 0.5 times 72.2 times 10 squared. Hopefully, if you've listened to me, if you've got a decent calculator, a good calculator, you might be able to, if you're lucky, just backspace and edit. And let me see if I can bring that previous line back, Mr. Dewick. Yeah, I can. And I can change the 10 to a 15. And I can change the 5 to a 10. And I got a typo here. What did I do wrong, Mr. Dewick? Oh, I got 2 squareds. Duh. Let's get rid of that squared. How do I get rid of that squared, Mr. Dewick? Like that. There we go. Do you get 4,512.5? Joules. Now, going 15 meters per second versus 5 meters per second should be 9 times as much energy. If I go 4,512.5 divided by, what was it, 902.5, I'll get, is it 902.5? Why do I get 5, Mr. Dewick? What's going on there? Is that right? Is it 4,512.5 or did I do it wrong? That's right. Okay. So you can't, because again, in this question, we went from 10 to 15. We're not going to get the 3 times faster, 9 times more. But if we had started at 0 to 15 compared to 0 to 5, 9 times more energy. But this also explains why, I'm assuming all of you have ridden a bike. And I'm assuming how many of you at least once in your life tried to see how fast you could pedal on a level road. You may have noticed getting going pretty fast, not that tough, but those extra bits, right? Increasing an extra 5 meters per second once you're going fast, way more energy than it took to get the first bit. This is why once you're going fast, it's so much harder to go faster, which you figure out when you're a little kid, but there's the physics of how come. Example 2, a rocket reaches a height of 340 meters when launched. If the top speed of the rocket is 85 meters per second, how much work does the rocket engine do on the rocket? Or how much energy did we need to supply this rocket for this to work? Well, Alicia, what's this question asking me to find? So my first thought would be force times distance. Don't write that down. Now, there's kind of a distance here, a height. I don't really see a force. I mean, maybe a free body, but I also see a speed. You know what, Alicia? I don't think I'm going to use that definition of work. Work is also the area underneath a force versus distance graph. Why? No graph. Third definition of work. Write this down. The change in potential plus the change in kinetic. What's change in anything? So this is going to end up being potential energy final minus potential energy initial plus kinetic energy final minus kinetic energy initial. Are any of these 0? We're starting on the ground. And depending on where we put our start point, I think we can make an argument that we're starting at rest before we press the button on the rocket. So I think this modified definition of work is going to end up becoming mgh final plus a half m v final squared. Do the m's cancel here? Why not? And you know what? That makes sense. A bigger rocket should take more fuel, more work. Yeah. Okay. So what's the mass of this rocket? 0.15. What's G? 9.8. What's H? Plus 0.5 times 0.15 times 85 squared. How much energy must be stored in this rocket engine if we're planning on doing this? And so we're starting to do a little bit of rocket science. This is actually a question I'll ask you when we go into orbit. The problem when we go into orbit is that G is no longer 9.8. It's changing. So we're going to have to modify this equation to come up with a cosmic potential energy equation that works anywhere on the universe, not just on Earth. And unfortunately, it's ugly. Just no way around it. It's on your formula sheet. You probably have another PE question under gravity, equation under gravity. What'd you get? Sorry? 499.8? Is that right? I'm skeptical. 1041? Point? So 1042? Let's go 1040? Joules. Example 3. A 1,250 car, a 1,250 kilogram car is traveling at 35 meters per second over level ground. I would probably underline the phrase level ground because that tells me my change in potential energy is, remember that. Kiana, what's A asking me to find? So my first thought was work equals force times, that'd be great. Do you see a force? In fact, what's part B asking me to find? There's a question in front of what's creating the force. Bet you I can't use a force. I'll probably use my answer from A to find part B. Okay. It's also the area underneath a force versus distance graph. Did they give me? No. Kiana, what's my third definition of work? Sorry? Read me the work energy theorem. How come I was lazy and just wrote change in kinetic? I noticed level ground. By the way, you can write them both out, and usually I do because these questions can sometimes be really complicated, especially if we were doing the Physics 12 version of this unit. I would be giving you way more complicated questions, but for now. And Kiana, what's changing anything? This is going to be a half mv final squared minus a half mv initial squared. Are any of those 0? What? Final. I'm going to get a negative answer. Yes, we're doing negative work because the car has to lose energy to come to a stop. I'm okay with that. I'm going to get negative 0.5 times 1250 times 35. Don't forget the squared. Manraj, redeem yourself. Tell me what the correct answer is this time. Negative 76565? Negative 76565. That? Okay. On a test, if it was multiple choice, I'd probably round it to 3 sig figs, so I'd write it as negative 700,660 joules, but we're going to use this for part B, I already noticed, so let's carry the sig figs. In fact, Kiana, what did you say part B wants me to find? What is the force? I mean, there's kind of an M. Maybe I could figure out A. Maybe I could go F equals what? But wait a minute. What did we just find? Is there an equation with work and force in it? Let's try that. Kiana, can you look at the equation that has work and force in it? And can you get the F by itself, please? Let's see. Work is force times distance. How would you move the D over? What's the D doing to the F? So, okay, you said multiply, you said divide. Which one of those is absolutely positively correct? What are you going to do with the D? Yes, thank you. Work divided by distance. Yet another definition of force. We've got a zillion of them. I guess 82. What's the negative telling me? It's telling me that the force and the distance are acting in opposite what? Directions. Okay, so I'll probably chuck the negative in my answer for friction because negative friction doesn't really make sense, but it's telling me the car is moving forward, friction's moving that way. That's why you're losing energy. But they are in the same plane, so I can use my nicer definition of work. What'd you get?
Negative 9,836.9.
I'll go negative 9337. Oh, but we're going to chuck the negative here because forces are positive. I mean, you could make that direction negative, but whatever. What's creating the force? What force is this? It is friction. What does C want me to find? Okay. So if in physics 12, I would have no problem giving you the first line and then asking you what's the minimum coefficient of friction necessary to stop it in 82 meters and having you clue in, oh, they didn't give me a mu, they want me to find a mu. You know, I think it's all this work. Anyways, oh, what's an equation for mu? What does mu equal? There is an equation with mu in it. Get the mu by itself. What does mu equal? Friction divided by the normal force. Now friction, I'm going to use my answer button. I'll write 9337, but you're all going to use your answer button. Ooh, I don't know the normal force. Are we on level ground?
Yes.
Do you know what the normal, I'm pretty sure this time it's what? It's mg. .76, anybody else?
Yeah.
3 sig figs, .76 what? Is that .762? Is that right? Rounded off properly? Units. Oh, yeah, mu no units. You might recall way back last year in Physics 11, some of you first quarter, I did a question early on in kinematics, and I'm always trying to show you where you can use stuff, where we looked at an RCMP investigating a car crash scene. And we wanted to figure out how fast the car was traveling before it started to skid. And I had to have the cell phone pick up the sound of the skid because, Rachel, you didn't know much physics at that point in time. I don't know if you remember, but I promised you at that point in time, we'll revisit this question and we'll be able to do it just from the length of the skid marks. We don't have to have that incredible coincidence of the cell phone picking up the sound of the skid because that gave us time. Here it is. I would have got to this last year normally. An RCMP officer is investigating an accident. A car struck a pedestrian at a school crosswalk. No witnesses. The RCMP measures the coefficient of friction on the road right there to be 0.65. There's instruments that you can use to measure that. And then measures the skid marks to be 49 meters long. Should the RCMP press charges against the driver? What? So I heard someone murmur it. I thought I heard somebody murmur a physics term that we needed to find here. What's this question wanting us to find? What would we need? Which one? Okay, I think it wants us to find VI. We're going to do it with speeds, I think. But yeah, I think it wants us to find... What's VF of any car crash ever?
0.
I got a distance. I got a mu. Does this question imply there's a hill at all?
No.
Then I'm going to assume level ground. If I gave this to you on a test, I would make it level ground. We could solve this now. We have enough information that we could probably do a free body diagram. We could probably find the force of friction. Who's winning? Who's losing? We can find A, and we could then find VI. But I'm going to show you a slightly different way to do this. We're going to do this in terms of energies and work. I'm going to start out by writing out work equals work, which may be the most obvious equation I've given you all year. Well, duh. But now we have two different ways to write work. We can write it as force times distance, and we can write it as change in potential plus change in kinetic. Oh, what did we say the change in potential was? Which force is doing the work in this question? Which force is bringing the car to a stop? On the right-hand side, what's change in anything? Are any of those zero? So we're going to end up with this. 0 minus a half mv initial squared. Now, this force of friction is also in the opposite direction of distance, so technically it's negative because it's in the opposite direction. My point is we're going to chuck the negatives on the next line because we're just concerned about magnitudes here anyways. Okay? I got a negative on the right, I got a negative on the left. It's going to be a negative divided by negative, which is a what? Positive. What am I trying to find? So, really what I have right now is this. Friction times distance equals mvi squared over 2. Friction. Help me out. Friction is what times what? I don't know the normal force. I think it's mg. Now, if this was on a hill, they would actually measure the angle of the hill, and they would do the components. Totally doable. I'm not going to throw, because this is physics 11, they wouldn't have known about components yet, but since you're physics 12, you can ask yourself, could I handle this on a hill? Yes. Am I going to give you one on a hill? No. But in physics 12, would it be one that we can handle? Totally. But we're on level ground right now. So we're going to get this. Mu mg times d equals mv initial squared over 2. Oh! Huh. What? Turns out I don't need the mass of the car. In fact, if this was a hit and run and I didn't even know what the car was, I can still figure out how fast the car must have been traveling. Kind of nice. What am I trying to get by itself? So, and then I'm willing to bet if you're a car crash scene investigator, the same way you've all memorized VF equals VI plus AT, this is probably one they have at their fingertips. VI is 2 mu g d square root. That's the car crash equation. Hey, what if it's snowing? What happens to mu? Which means it gets smaller. It means for the same speed, you need a bigger distance to come to a stop. And you can see it's not a one-to-one easy linear relationship. There's a squared and a square root. This explains why people are so bad at driving in slippery conditions, because they kind of think ballpark, oh, I don't have half the braking, I'll probably need twice the distance. No, no, no. Way more than you realize. What do you get? Let's plug in numbers. Square root of 2, what was mu, 0.65? Times 9.8 times 49. 2 times 0.65 times 9.8 times 49. You get 25 meters per second, basically. Is that right?
Yeah.
And I heard, did somebody already convert that to kilometers per hour?
89.
Okay. So certainly you can press charges. And again, if the person was killed, you could probably push for vehicular manslaughter, because going 90 in the school zone, come on. Okay. So I felt bad last year that I couldn't complete my promise of, I did promise you when I did this last year. Some of you might even remember the question because it's one the kids always like. We didn't get a chance to revisit it without the cell phone coincidence, but there you go. Alrighty, put your pencils down. Let's try to see if YouTube makes me take this down or not, Mr. Dewick. What is the motorcycle video, Mr. Dewick? Is it under... Oh, yeah. This is a dumb driver. Yep. I guess you're going to miss a cool video, but okay. So, I picked this video because the driver was dumb enough, but convenient and polite enough to show me the speedometer. How fast is the driver going? Units. Look very closely at the inner speedometer. I think those numbers are larger. I think this is an American-made motorcycle. That's miles per hour. Okay? Like if you look real close, I'm pretty sure these numbers are larger. As I look, right, that's 110 right by the 70 there. Okay? This is miles per hour. How fast?
Lots.
No, as a number exactly? What did we say? Can you write down V equals 220 mph, please? We'll do a conversion in a second. Rider slowing down. What type of energy are they losing? Where is it going? Got to go somewhere. I'd like to know how much energy is being bled off. I'd like to know how much. So let's revisit this again, and you're going to need to get out a smartphone and open a stopwatch app, please. And what we're going to do is we're going to start our stopwatch right when you hear him start, or her, probably him, being stereotypical. Dumb drivers, usually males. Start to slow down. So ready? Get your stopwatch ready. Wait for it. Kind of leveled off, and conveniently he's leveled off. You can put V final is 100 miles per hour. Folks, you can write down Folks, you can write down V final is 100 miles per hour. Nice convenient number. Around how long, how much time, Owen, did you get?
Not way.
15, 16? So because we're doing very rough timing, let's say 16 seconds. Okay, so we got time. So let's jot down our data. Time was what? 16. What was VI? 220. And what was VF? Okay. We could do a full-blown conversion, but I'm fairly lazy. Convert 220 miles per hour to meters per second.
That would be 98.35 meters per second.
Convert 100 miles per hour to meters per second.
It's 44.7 meters per second.
I have a handy trick I've learned over the years. I know miles per hour is roughly twice as big as meters per second, so I knew this answer was going to be around 50, 44.7. I knew this answer was going to be around 110, 98. We're close. Anyways, okay. First of all, what does A want me to find? How much energy is, how am I going to figure that out? Okay. You know what A is actually asking me to find? First of all, is there a change in height, change in speed, yucky curve? I'm not going to go law of conservation of energy. What this is really asking me to find is the work done by friction. So I'm actually going to go W equals force times distance. Was there a force given in this question? Was there a distance given in this question? Scratch that version off. Was there an area underneath a force versus distance? Scratch that off. You know which definition of work I'm going to use? I looked at that road in the video. I'm fairly sure we can say level ground. It looked pretty level. Okay. What's changing anything? So this is going to end up being a half mv final squared minus a half mv initial squared. We're going to get a negative answer because the motorcycle is losing energy. Let's see what we get. Oh, we don't have a mass for a motorcycle, do we? Or did I say assume a mass in the question? I did, 300. I did some Googling at some of these street bikes and did some, okay, on average, they seem to have about that. Okay, so we can go 0.5 times 300 times 44.7 squared minus 0.5 times 300 times 98.35 squared. And I get negative big number. I get negative 115,1194.875. Is that anybody else? Okay. I'm going to write negative 1.15 times 10 to the 1, 2, 3, 4, 5, 6th, but I'm going to keep this on my calculator because I think we're going to use it some more. Negative 1.15 times 10 to the 6th joules. Why negative? Yeah, and so again, this is not a vector negative. This is a scalar. The number is decreasing. The magnitude is decreasing negative. But now for the remainder of the question, I'm going to chuck that negative. I'm going to ignore it. First of all, where'd that energy go? Heating up brakes. Ah. Ooh. Ha. Rachel, what's C want me to find? Power. Well, power is either work over time or it's force times constant speed. Oh, is there a constant speed in this? Nope. Ooh, what did we find in part A? Work. We can do it that way. So it's going to be, I'm going to write 1.15 times 10 to the 6th. I'm going to use my answer button. And what do we say the time was? Okay. And I'll ignore the negative that kind of continues on through my calculations right now. But this would be a power loss, so you could think about it as negative if you really wanted to. But it's going to be this number divided by 16, and I get 72,000 watts. Did not get that? Of course it's divided by 16 because it's work overtime. Did you go times by 16? So on your calculator, go divide by 16 to undo that, and then divide by 16 again, and you should end up where we did. Or you can cleverly divide by 16 squared. That should fix it. Is that okay, Alicia? Okay. How many 60-watt light bulbs could... Better yet, instead of how many 60-watt light bulbs, I'm going to ask... How long could we power a 60-watt bulb? So not how many can we light up. I'd like to know how long could I run a light bulb from that? So I guess that's asking me to find time, the time in the power equation. So I think, ooh, I want to get this T by itself. Where is the T right now? Ugh! I'm going to say, I think time equals work divided by power. Remember, stuff moves diagonally. Remember that trick I showed you at the beginning of the year? So it's going to be this number here, which I still, boy, I should have written down more sig figs. I still have it as 115, 1195. You know what? Let's just use negative 115. Let's use 115. Sorry. Let's use 1.15 times 10 to the 6 because I forgot to carry the sig figs. But I'll divide by my answer button here. Wait a minute, wait a minute, wait a minute. Are we doing this right? Sure we are. Except what's the power I want to divide by here? Not 72,000 watts. So I'm going to go 1.15. Whoop. Come on. 1.15 scientific notation button 6 divided by 60. I could run a light bulb for that many seconds. How would I convert that to minutes? How would I convert that to hours? I could power a light bulb for over 5 hours in the energy wasted in coming and slowing down. So this is why hybrid vehicles, electric vehicles, one of the reasons they're so much more efficient is instead of the energy going into heating up the brakes, most of this energy goes back into recharging the batteries. It's a good system. I did the conversions. I'm not going to ask you something like D on a test, but I think it's just kind of a neat question. I saw this video. I think they were able to track him down because he posted on YouTube and they figured out who it was, and you know, because that's just dumb driving. One more. I know in Physics 12 I like example 4, I like example 4, I like example 4. I can't remember if on the Physics 11 test I like example 4, I like example, but I'm going to say just in case, I think I like example 4, I think I like example 4, I think I like example 4. A rocket car, ooh, rocket car. Initially at rest, I would probably underline the word at rest. On a frictionless horizontal surface, I might also make note of that, because if we're horizontal, what's our change in potential energy? Okay. The engine is ignited, and the graph below shows the thrust force versus the distance traveled. I guess we get a constant thrust for a while, and now the engine is dying out. Make sense? Oh, A says, why do you think the force decreases after 15 meters? I guess I kind of answered that. What's happening? I think the rocket propellant is burning out. Engine is burning out. Francesca, what's B want me to find? The speed. How? What? I mean, okay, I got VI is 0. I mean, maybe there's a D of 20. Huh? Okay. First of all, did it say find the velocity? Or did it say find the speed? Hello, everybody. Did it say find the velocity? Or find... That's suggesting do a scalar approach. Okay. How am I going to do this? I'm going to be clever again. I'm going to say work equals work. And on the right-hand side, I'm going to say change in potential plus change in kinetic, my most flexible definition of work. On the left-hand side, I'm going to say, this time they gave me a graph. It's the area. Ooh, what did we say the change in potential was? Because it said horizontal. Gone. What's change in anything, Manvir? Sorry. Manraj, I did it again. Okay. So this is going to be a half mv final squared minus a half. Oh, wait a minute. What two words did I underline? From what? Ha ha! This is the power of all three of these definitions of work when you start using them in the same equation. You can figure out a lot with very little information. Oh, what's the area? I guess the area is going to be, because it says to 15 meters, it's going to be that there. What shape is that? How do you find the area of a rectangle? It's going to be 15 times 160. Rectangle, 4 sides, Owen. How would I get, oh, it wants me to find speed now. I can get the V by itself. I think it's going to be times by 2 or divide by 0.5. Times by 2, divide by M. Did they give me the mass of the car? Okay, good. And then square root. I guess V is going to be 2 times 15 times 160 divided by, what was the mass of the car? 5.2. And don't forget to square root. It's the work energy theorem with a bit of cleverness is a very powerful tool because it combines work and energy, and because work also includes force times distance, it pulls in some of that. Because energy includes V's and it's pulling in some kinematics, it's really putting a bunch of stuff in one nice tidy line. You might be able to solve things without it, but it would take about 5 or 6 more lines of, no pun intended, work. What'd you get? 30.4 meters can't be right. Meters per second can be right. Oh, maybe I thought I heard meters. What? Okay. C, same question, but now we're going to find after 25, so it's going to be the entire area. But it's going to be a pretty similar argument. We're going to say, hey, you know what? Work equals work. On the right-hand side, it's going to be a half mv final squared. The initial is 0. On the left-hand side, it's going to be the area, which is going to be the rectangle, plus, how do you find the area of a triangle? It's on your sheet if you blank out, but...
Base.
Huh? Base times the height, or base times height divided by 2? What's the base of the triangle? 10? What's the height of the triangle? 160 divided by 2? This is about my limit of getting the v by itself. I think before I get the v by itself, I would just crunch this and turn it into one number. I would get my calculator out and I would go 15 times 160 plus 10 times 160 divided by 2. Oh, the left side is 3,200. I would say 3,200 equals mv squared over 2. Half mv squared. Is that right? Is it 3,200? Yeah. And now, times by 2, divide by m square root. Is the answer going to be bigger than 30.4 or smaller than 30.4? How do you know? The rocket was still going. The force was decreasing, but there was still an unbalanced force, so it's still accelerating. So I'm expecting a bigger answer. A bit of a built-in error check there, right? 2 times 3,200 divided by 5.2. Oh, 2 times 3,200 divided by 5.2. Square root, answer button, and I get 35.1. So some of that is what you needed on the take-home quiz to do 4B, and I apologize, I somehow missed that. So take-home quiz is due tomorrow. We're done the unit tomorrow. All I'm doing is marking the take-home quiz, but the rest of the class will be yours to work on missing homework. From this assignment here, I think you can try number 1, number 2. 3 is good, 4 is good, 5 is good, 6 is good. I'll skip number 7. Number 8 and number 7. Go figure. 9 is good. I'll skip 10.
The new Boeing 747-8 is a massive machine, designed to take off at close to 1 million pounds. Through months of flight testing, the airplane has shown plenty of power on takeoff. But how would it handle all that energy if it had to suddenly stop?
In the emergency event that we have to make a rejected takeoff at these heavy weights, it takes a long distance for the airplane to stop. It's just like in your car.
Captain Kurt Vining and the Boeing Test and Evaluation Team are about to put the airplane through the ultimate rejected takeoff, or RTO. First, the crew installs a set of 100% worn-out brakes.
So it's down to the stud. So if you ever have your own brakes, they've got a machine down, and so there's just basically no material left.
Technicians also fuel the airplane up to maximum takeoff weight of just over 975,000 pounds.
This is not a conservation of energy, Gigi, question. This is a work question. M does not cancel, so let's add as much mass as possible.
At the start of the runway, Captain Vining begins the takeoff roll as usual, pushing all 4 engines to maximum thrust.
Getting a lot of kinetic energy.
But just as the airplane is going at over 200 miles or 320 kilometers per hour, he slams on the brakes.
What's that kinetic energy going to get transformed into? A phenomenal amount of heat. Wait for it.
To channel maximum energy to the carbon brakes, the pilot cannot use the thrust reversers.
Oh yeah, because normally they can reverse the engine, but this is
The whole
worst
intent
case
is to
scenario.
demonstrate you, under the worst conditions, you could safely stop the aircraft.
The brakes, made by Goodrich, do exactly as they're supposed to. In fact, the 747-8 stops earlier than the team had hoped, beating the target by more than 700 feet or 200 meters.
Can you see the hubs glowing
But
red
stopping
hot?
is just half the challenge. Now the airplane must prove it can withstand the tremendous heat that built up in the wheels, estimated to be more than 1,400 degrees Celsius.
That's the metal glowing red hot.
And it's a simple physics problem. We have to turn that kinetic energy into heat in the brakes.
As expected, smoke pours out from the brakes as they glow a bright orange. Still, the firefighters who are standing by can't do anything but watch for the next 5 minutes.
And that's to simulate that if you were at an airport, you had an RTO, you wouldn't necessarily have the fire department right there. So to demonstrate that, worst case would be 5-minute response time for a fire department to get to the airplane.
By design, special fuse plugs in the tires are activated, deflating the tires before they explode. Finally, at the 5-minute mark, firefighters move in with plenty of water. While the tires and brakes will have to be replaced, the rest of the airplane is perfectly fine. No sweat, even for the flight test engineers who were on board.
It went amazing. The decel rate was exactly what we expected. Great stopping, no major faults.
Slamming on the brakes so the new 747-8 can continue moving towards certification and delivery.
So a nice example of conservation of energy being transformed from kinetic into heat.
Is that video on YouTube?
I found it on YouTube, yeah. As well as this one. All right. So now we're going to fire a gun at a physicist underwater. Now the kinetic energy is going to go into deforming the water, force times distance. Will the water apply enough of a force times distance to reduce the kinetic energy to 0? Don't try this at home. Hopefully that was a fairly Captain Obvious moment there, but don't try this at home. That's him going, hey, I did the math right. So again, a nice example of the law of conservation of energy. This time, the energy is going into deforming the water, right? Force times distance.